Hello, everyone. Good day. Nice to see you here.
Hello.
I am Davide Pastorino from HPC Systems, and I am a solution architect.
And I'm Diego Bacchin. I'm an HPC cloud architect at the Do It System, part of Do It Now Alliance.
Oh, the presentation tool, I think we're missing. We're missing the presentation tool. Yeah, sorry. So we'll be talking about a Kubernetes solution we did for HPC Services for a customer that asked for not traditional solution for this management systems. So thank you so much. And it's let's see. Nope, not working. Doesn't seem to be working. Sorry. Oh, okay. Here we go. It's a bit.
It is a bit.
Yeah. Okay. So, Do It Systems, we are, we are the most prominent company in HPC Services. Sorry, in Italy, with more than 20 years of experience. We are part of the Do It Now Alliance. All right, which is okay. Thank you. And we support our customers with delivery of HPC solutions and support services, and from the planning stage to the implementation phase and the support system. So as I mentioned, we are part of the Do It Now Alliance. We have the Italian branch actually, and these are all the other countries we work on. And we are servicing HPC customers throughout Europe with many customers, many clients, more than 20 years or 30 years of experiences. And we are more than 110 people working on HPC systems, most of them technicians, some of them supporting staff. And we have more or less 5 clusters in the top 500 installed currently. And today we are talking, as I mentioned before, about a Kubernetes solution for HPC management services. And the context of this installation is a medium-big cluster, somewhat like 1,000 nodes, that will be used for scientific research. And that is hosted in one of Italy's most prominent data centers. And we are working as contractor on behalf of Lenovo. Yesterday, you had a presentation from Gilad Bergman, which is our partner in this installation. And what was the challenge that the customer asked us to take on? It was sorry, the delay. Okay. They asked us for a lot of requirements. So basically, they wanted to have a highly available system that was up all the time, even for updates, that needed to be scalable in order to support all the nodes, and also to collect all the performance metrics and data from the nodes in a real time. We needed to have a way to export those data in a massive way with a single API call, so possibly moving gigabytes of data with a single action. And also have some kind of predictive analysis for predictive analysis, anomaly detection, let's say, to find faults while they were happening and not after they happen. And for a traditional management system, we have 3 approaches. The first one is the more classical one, with a physical installation of 2 nodes with a pacemaker cluster for services to be in an active standby cluster, which is the most basic, actually, installation for highly available services, and a common storage, of course, to share the data between the two servers. And this is good for a small cluster, but it's not scalable, not very much indeed. It's just can be scaled up by adding memory, adding CPUs to the servers, but we hit a limit pretty soon. We can add a node, but still, since it is an active standby cluster, adding a node won't increase performance, for example. And we also have another approach, which is a virtualization one, in which you have a cluster of hypervisors managing virtual machines with services inside of virtual machines, and those are highly available between the underlying nodes. But of course, it's just adding an abstraction layer. You can scale out better. Still, the performances are bound to the single virtual machine where the service is hosted. And you have a lot of choices in this case with, commercial and open source software. But you also have not many choices for enterprise level for production environments and big clusters. So it's a trade-off between pricing and availability and reliability. So it's also that. And we also have the orchestrated container approach, which has a more complicated architecture on the first layer, on the physical layer, because we need more nodes. We need, for a production enterprise cluster with orchestrated containers, I think we need at least 3 control plane nodes and a couple of worker nodes at a minimum, but you can scale in the future by adding more nodes if you want to perform, to add services and make them perform better in some way, add replicas of containers and so on. And the containers can run basically on the worker nodes, and the control plane nodes will take care of just some things. So it's more complicated. It needs to be understood case by case if they are more cost effective in place of the other approaches. We have also commercial enterprise grade software here, which Red Hat OpenShift, for example. But you also have a very valid alternative in Kubernetes. There's an open source software freely available and usable, which is already very mature in this case. And we chose to go with Kubernetes, of course. And what enabled us to go with it? Well, basically, the provider, the hardware vendor that we are working with, provided us with a lot of hardware for this installation. The customer asked for at least 10 management nodes. So in designing the solution, we had a lot of choice on where to put things on and how we wanted to do this. So a lot of hardware meant that we can scale up the Kubernetes cluster basically up to whatever we needed for performance and availability. And also for software flexibility, because the Kubernetes solution also will enable us to have that particular data export pod, let's say, as an API endpoint, and the replicable services, so we can add the pods to deal with multiple queries at the same time, for example. And also we can support the anomaly detection system with an integrated AI-powered small loop that Diego will be describing to you later on. And we can train and serve the inference of these models directly inside the management cluster without impacting the actual operation of the computing cluster. And of course, we went to Kubernetes. So what challenges we were facing? Slurm and Kubernetes, because Slurm is the choice that the customer made for this cluster as a resource manager, are not quite ready yet to work together in a tightly coupled way, because you saw yesterday even there are efforts underway to make them completely integrated, but we are not yet quite there. We are still thinking about the approaches. There are different approaches right now, so it was quite a challenge to understand how we could do this. And the amount of data we were asked to store long term for the whole life cycle of this cluster were several tens of terabytes per year, possibly many hundreds at the end of the life cycle. So we were storing a lot of logs, performance data for everything, with a high resolution for the performance data indeed. And of course, full disclosure, we never did this before. This is the first time we had to implement this such a thing. So fortunately, we had also to design it, so we were more or less know where we were going. And the first approach we used was to divide the whole architecture in different levels, starting from the hardware and up to the operational HPC application. And actually, fortunately enough, we did not have to deal with the hardware and the base OS because, as we said before, Confluent did the distribution of the OS on the nodes. So we were just worried about the Kubernetes infrastructure applications and the operational HPC application that we were going to deploy. And we knew where we were starting from. So it's 3 control plane nodes, also 3 worker nodes with some certain amount of local storage, and a high-performance parallel file system that was integrated also with a CSI in the Kubernetes platform to manage a different application. And we wanted to arrive with a Slurm traditional installation with nodes accessing Slurm like always, like we do in the physical in a physical installation. And the predictive analysis, the monitoring system that will cover all the aspects of the nodes, from the CPU, the network, the power, and so on, with tons of metrics. The data export facility, as I mentioned before, and the prediction, the anomaly detection algorithm that we will need to identify data in this anomalies in this performance data. And of course, there's all the in-between levels is the main thing that we worked on. So we ended up designing particularly complicated. It got complicated rather quickly after we started. And we'll be explaining how we arrived there and how we will we integrated everything in the next few slides. So this is the journey. It's your turn. There you go. All right. Yeah.
The first step was to find the right software that we needed to deploy the Kubernetes infrastructure. We choose some software, we tested it, and we ended up with Kuspray. If it should be shown an icon with Kuspray. Yeah.
Got it.
Meanwhile, I'll continue talking. We used the Kuspray because we already tested in a previous project, a small project, but we used it and it worked very well. And this is the famous icon. Okay, so we start with a minimal OS installation, which is based on that Enterprise Linux 9. And we only need a network configuration and a SSH shell. The first thing that we have to do is to disable the security enhanced Linux and the firewall. Otherwise, Kubernetes doesn't work.
We know that is not the correct approach in a security environment, security concerned environment, but this time we are still in the lab. We are not yet in production. I promise we will check if we can make it work with Linux and or the firewall active. I don't know if we will manage, but it's not of capital importance in this space.
About firewall D, there are some tools on Kubernetes that is the network policy. So we disable firewall D in favor of the network policy of Kubernetes, or is more specific and more flexible than firewall D. The first thing that we needed to change on the Kubernetes was to create our inventory and set the IP, etc member name, etc address, so the cluster can work, and the Ansible host. The next step was to update some settings of Kubernetes, the interface regular expression, so the CNI could take the right interface, because in our case there are multiple network interface, and of course the Kubernetes service network and the Kubernetes pod network. The next step was to find the right solution for the network plugin, the virtual IP management, and the ingress controller. For the network plugin, the solutions that we have used was Flannel, because the customer required to use that. It's no problem because it required to zero to no little configuration to work. For have some kind of redundancy, we use the virtual IP management. So we are able to assign an IP to one of the nodes and continue to elevate service to the cluster. For the ingress controller, we go with Nginx ingress controller, which is a well-known tool. As I said, Flannel requires zero to no little configuration, and kubevip take us a little bit of time to work, because we started with a Helm chart installation, and we needed to apply some other configuration when we deploy service, because we prefer to assign manually the IP that we want. For example, assign IP also for the Nginx ingress controller. We choose to make a change the spec of the default Nginx installation, that is to install a daemon set type installation instead of deployment, because we want to be sure that there is at least one Nginx controller per node. So in this case, we are able to reduce the traffic overhead between nodes. For the main Kubernetes storage, we use Rook, which is an Helm chart that deploy the SF storage. And for the object storage, we first start using Mini.io, but we have found that it requires a lot of resources and has too much feature for our needs. So we go back with the Chef implementation of the object storage, which is a Rados gateway. And in our case, we have only one point to manage everything about the storage. Rook was installed on a worker node, and it exposed using Chef the local storage SSD. And the only thing we needed to change was the local disk that we have formatted, and nothing more. And in this way, with this step, we have completed the first level, which is the object storage, the virtual IP, and the Nginx ingress controller.
So, all right, and for the above level, in the Kubernetes application, we are talking about tools that we will be using to deliver the services at the above level. For example, we knew instantly that we needed an internal container registry, because, as you said before and yesterday, that we don't want to pull images from the internet all the time, and we need to build our own images, and we need a container registry to keep them available for the whole life cycle of the platform, so we can plan for upgrades and so on. And of course, we went to choosing Harbor, which is a mature product, and with particularly good security features, such as vulnerability scans directly in the image, which is very interesting to have. And it was not the easiest process to install. It required some certificates to work properly within the cluster itself. We did not have a certification authority on the lab, so we used the internal Kubernetes CA to generate the certificates and then import them on all the worker nodes and the control plane as well. And after this, we just needed to restart the kubelet and the containerd services, and everything went good. So it was working like we planned, and we took, I think, half a morning to do this, something like that. All right. And for internal configuration management, we resorted to have the simplest thing that we can think with a graphical interface for Git development, which is Git, which is a particularly lightweight distribution with a lot of features, actually. And I don't know if you know it. Its interface resembles the one of GitHub, but of course it's way less feature rich, and still it's very useful in our case. This is to safely store the configuration of the Kubernetes cluster itself. I know it's not the best practice, because it's a snake eating its own tails if you store the configuration inside the thing where you're trying to configure, but we are still planning to use it inside the inside the cluster to manage the operational applications. And we will have a backup of this Git on an external device, an external repository for the customer to track the changes as well. And why Git? Because versioning in this case was a must, because we needed to have a solid control, a solid change management control procedures for the whole infrastructure, for the whole life cycle of the infrastructure. And this is everything we have for the level 2. And we added, as I said, the Git repository and the container registry. And everything that is above is actual HPC management software. So, thanks for you.
We start with the log collection stack. We use Loki instead of the Elasticsearch stack, because Loki is more performant and requires less resources than the Elk stack. The log collection is made out of the box on Kubernetes, but for the compute node, we install the PromTail agent and configure it to send the log to the Loki service. All the logs are viewable from the Grafana dashboard, so we are able to have a single point that is Grafana to view logs, metrics, and other stuff. So they're very useful for the system administrator. The Grafana Loki was installed with the Helm chart, and all the object storage is provisioned by Rook. So we have another point, another unique point to have all the data. This is a sample dashboard to show the logs where we are able to filter based on custom pattern and have a quick view. The next step was obviously the Prometheus with the metrics collection, and we installed on each compute node the node exporter, so we're able to collect all the metrics, and also we installed the Slurm exporter inside the Slurm CTLD as a sidecar, so we are able to scrape all the internal metrics and collect them and make anomaly detection even on that. We have some dashboard on Prometheus that you have already seen, I think. And
it's just so they're very detailed. So the optics of the resolution of the data is very fine. So it's it's a lot of data.
Yes, especially with the thousands of compute nodes. We need also face another issue that we need to keep the storage, keep the data for a lot of time. We at the moment don't even know how much time we need to keep that. So we started to compare two products for the long-term storage, the well-known Thanos and the new solution that is Grafana Mimir. We make some tests with Prometheus, which send the data with the remote write features. And all the data is stored, even that, on the Rook object storage. And we have seen that Thanos requires a lot more storage than the Grafana Mimir. It takes 25% more than the Grafana Mimir. And so we go with the Grafana Mimir because with 1,000 nodes, we have a lot of data, so we take that. Now, in the job. For the database solution, we have looked on the first with the Vitesse, which is a MySQL replacement for database. It's horizontally scalable and came out from YouTube and big company. We also look for MariaDB cluster, and for the Slurm configuration and management, we take MariaDB because Slurm doesn't support off-the-box Vitesse because Vitesse lack of some functionalities. But we use Vitesse on the anomaly detection part.
And as for Slurm, we have followed the approach of non-integration with Kubernetes. I know it sounds strange, but what we did is actually containerize Slurm CTLD, as I said, in a standalone container, as well as Slurm DBD in another container, and working them as pods to connect to the MariaDB cluster that Diego was talking about. We tried to use Vitesse, but as he said, some features were lacking, so it's not yet ready. And of course, we installed the Slurmd on the nodes physically, not within a container in this case. And the CTLD and the Slurmd will communicate through the Kube VIP virtual IP, which is exposed also as a DNS records in the DNS system of the Kubernetes platform. And it works like any other cluster, so it worked without any problem. As they didn't see any difference as Slurmd in the logs. There are no errors, particular errors. It's working very good. And of course, we installed also the node exporter for specific metrics from Slurm into Prometheus. And the thing is, everything we said so far has been collected in a single Helm script. And this is the most exciting feature for me, that we'll be able to replicate the whole infrastructure just with this Helm script on another Kubernetes cluster wherever we want. And basically, we just need to set a few parameters in the distribution of the script, and we can replicate the structure everywhere. We did all this work in a lab, actually. We did all this work in a lab, and we are going to use this script to deploy it in a gateway system, which is the first installation we'll do probably, and in the production final system. So it's going to be reused very quickly and very soon. So, all right, if you want to go back to the presentation.
The next part was to visualize some data about the Slurm. So we have some graphs about the Slurm exported metrics. So as we say, we are able to make anomaly detection and also view all the metrics in real time. We have completed now the level 3 part, but as you can see, there is something that it's missing right there. And this is the work in progress part. This is the anomaly detection feature that we have installed on the cluster. We start obviously with the Prometheus, which has all the metrics that we need to get. And we start with a development phase where the data scientist has a Jupyter Hub inside the Kubernetes cluster, where he can train, develop, and manage the models. But the most important thing is that all the procedure to training the data is saved on the Git repository. So we have a versioning of the procedure to train the model. And the train is automatically done by the tool partial flow, which is always synced with the Git repository. And in our case, we run the training steps every day using the last 2 days of data. And it creates a lot of training job based on the amount of model, one per node, etc. And it takes the data from the Prometheus and Vitess. As I said before, we use Vitess as an inventory, so we have all the compute nodes, all the information about the node, etc. And also, after training job, when it's completed, all the models are stored inside the object storage of Rook. And this is the training part. The next part is the prediction feature that is always made by Airflow, which launch a lot of job of prediction in a 5-minute window, and take the data from Prometheus and Vitess, and after save the anomalies data on Vitess. We choose Vitess for the anomaly detection because save the data about the anomalies on Prometheus is difficult on the first step, and it's very difficult also to manage. And in this case, we have a part of development that can cause issue on Prometheus because for example, if the developer make an error, etc. So we prefer to make everything on Vitess, so we are able to manage the data, fix, etc. And this is a dashboard of fun. On the first part, we have the event time, the anomaly detection, and also the component that the models think that is an anomaly. And we have an historical view of the anomaly score of the anomaly. That comes.
We don't have much data yet because it's still in the lab, but once we have 1,000 nodes, I mean, it should be more, I think...
Yeah. It will be more interesting on the production.
More sense. Yeah, let's say. All right.
Because in the production, we also want to predict the data with Slurm. At the moment, we have no Slurm data, so
yeah,
it will be interesting correlate application and anomaly.
I mean, it will not be a single model. As I said before, it's a set of many training jobs in parallel, because we are planning to split the models, the inferencing models between different areas. So one for the power envelope and the thermals, one for the CPU and memory subsystem, one for the network, and so on. So we will have different models with feeding us back data about the anomalies in different areas.
Something that I have not said is the Airflow has a lot of integration with a lot of providers, like for example AWS, etc., and a lot of features. One of them is that all the logs are saved in bucket, so can be viewed and can all relaunch the training job, the prediction, based if there are some problems. And for example, it also has out of the box the encryption feature. All the database, all the credentials are all encrypted.
Yeah. All right, let's go. Oh, did we turn off? Everything turned off. All right, thank you. Sorry. All right, and okay, the outcomes so far, because we are not yet done. This is still in progress, as I said. And what can we expect out of this installation? So we started wanting something that was that needed to be highly available, and we got this because Kubernetes has this as intrinsic. As well as scalable. So this is also true because basically all the services minus the Learn CTLD right now, we will see in the future. Every other services is scalable with multiple pods and multiple endpoints, so not worried about this. And we have the data extraction point with an endpoint from Prometheus that can manage the extraction of historical performance data and logs and so on for the customer to import in another system. And we're still working on the prediction and anomaly prediction tool, but so far the results are encouraging, and we expect it to work without too much of a hassle in the future. And okay, it's time for questions. Thank you all for your attention.
Any question from the audience? Whoa, yeah, they.
Yeah, you sure? Don't be too evil, please.
No. So it's amazing. So so the incorporation of Airflow into this design architecture looks really good. So one of the things that we worry the most is that kills somehow the efficiency of the cluster as a whole is underestimating or overestimating the runtime limit of the jobs. It limits the ability for the virtual system to assess potential jobs that can run as a backfilling, to fill up gaps, and at the end of the day, at the end of the journey, to maximize the return of investment. So this has an impact on every level. So in a situation where you are in a cloud bursting situation, so this will give more opportunities to backfill some potential jobs. So now that you have Airflow into this design architecture, I was wondering if you have a think about retweaking the runtime limit for the users that have no clue about how long the jobs will run.
Yeah, well, one thing we like about Airflow, but Diego is more skilled to me about this, but one thing I like very much on Airflow is that we can incorporate basically any logic in it. So we can, I think the platform will evolve a lot in its production time. And if the customer will ask us to do some optimization, definitely we'll be using Airflow from getting data, analyzing with the existing data, and change the logic in how the cluster works, even the scheduler works, such as runtimes and so on. So it's going to be a powerful platform to configure for sure. To add something? Okay. All right.
No. Yeah. Really nice talk. I have a couple of questions.
Sure.
First one of them maybe you cannot answer because it's like, the purpose of this cluster is to be shared among many users.
Yeah.
Okay, great. And the other question is, I saw xClarity was for doing energy measurements in the cluster.
Yeah. It's that's still something in progress, but energy management means in that case it's meant to be it was in the energy management part of the project, because we will be using actually here as an energy management tool. We still haven't integrated it because we're still in the progress for that. But Xclarity will provide actual readings from the BMC of the servers into Prometheus as well. So we will be able to detect any changes in power absorption and so on. And also we'll be able to control it to change, if needed, the power envelope of the nodes in hardware. Yeah. Yeah. Yeah, Xclarity is the BMC of Lenovo, let's say. Yeah.
Oh.
No, it's not software.
Okay, yeah, but the problem is like if you want to apply the same solution that you just have developed for a different vendor.
Oh, in this case, we just need to, it's the integration for the Prometheus metrics. So you just need to do an exporter for the other BMC, and then we can gather data and send it back via, I don't know, probably controlling Confluent, so with Redfish. Yeah.
What then the IP layer that's not what?
Yes.
Okay, so I know who to ask questions afterwards.
Thank you, Gilad.
Thank you.
Hi, thank you very much for very interesting the talk. Okay, we have a question. Which is your pros and cons, or your advice if, for example, a Slurm installation using containers, not the whole Kubernetes stuff, let's suppose something smaller, and just for easy of use and installation, let's suppose that we want to install in Docker and just in Docker containers. If you have any advice, pros and cons, thank you.
Do you want to talk about this, or should I?
Yes, some advice on the Slurm CTL installation was that we created the Docker image, not compiling the software, but we have compiled the RPM on a compute node with all the functionality, and then we created the image starting from that RPMs. It's only advice that we have, and use the MariaDB that is supported.
Yeah, well, one thing we found at the beginning of the project when we were trying to containerize Slurm was a container Docker recipe that would compile every time Slurm from scratch. And as Diego said, that was a bit of a overhead. So first of all, we decided to compile the RPMs in a traditional Slurm installation way, activating all the dependencies and then incorporating them into a base container with the same base host that is running on the nodes. So we can use the same RPMs on the nodes for the physical installation and inside the containers for a containerized installation. Nothing particular comes to mind for Slurm in this case. Yeah, configuration file is shared, of course, between on the parallel file system between all the nodes. So this is a single point. Manj key, the same thing. And of course, we need to also have the same users and the same identification and accounting and authentication management for the Slurm containers as for the nodes. So that's the only one thing.
Any other question from the audience? So it's my turn.
Thank you so much.
Well, I have one. We have
you got one? All right.
Yes.
Was
You show the anomaly detector.
Yeah.
Which anomalies are you expecting?
Let's say we needed a tool to help the system administrators find anomalies in the cluster at runtime. I mean, they expect to have some power fault, some memory fault, some disk fault in the life cycle of the system, and they want to catch it as early as possible. So if a node is behaving differently from the other, for example, if the same job runs with different performances on on two nodes, then we need to catch which node is acting differently and why. So it's it should be a tool that they will use to identify which component is failing or is behaving abnormally, and at an early stage, so they can drain it as soon as possible and basically not having any black holes in the cluster that eat jobs, something like that.
Okay, thank you. So let's thank again to the speakers.
Thank Thank you.